Okay, so decomposition reactions, as was mentioned before, these are kind of the opposite of combination reactions. Combination reactions are two or more reactants coming together to form one product. Decomposition, typically you have one reactant breaking down to two or more products. So here we have an example of the Hoffman electrolysis of water, where we have water decomposing, right, and water is a compound, into its two elements, hydrogen gas and oxygen gas. And the nice thing that we notice is there's actually a stoichiometric factor in here. We haven't talked about stoichiometry. We'll see this later, but we'll see that there's twice as much hydrogen as there is oxygen, which is shown in the balanced chemical equation with the coefficient of 2 versus water, which would just have 1. And we see that with the volume of the gases in this picture here. So again, we have one reactant breaking down to two or more products, or you can think of it as decomposing. So there are certain examples of decomposition, and one example is where we see a metal and a nonmetal breaking down to a metal and a nonmetal. Really what I could have put here is an ionic compound. Right, so in this example here we have mercury 2 oxide breaking down to mercury and oxygen gas. Another example of a decomposition are metal carbonates, and they can break down to metal oxides and CO2 gas. So the metal carbonate we have here is calcium carbonate, and it breaks down to the metal oxide calcium oxide and CO2 gas. So again, in every single one of these sample decomposition reactions, we have one reactant breaking down to two or more products. The third I want to bring up is, for example, metal chlorate. Metal chlorates break down to metal chlorides and oxygen gas. And we see here that calcium chlorate breaks down to calcium chloride and oxygen gas. So this is just so you get comfortable seeing different types of decomposition reactions and if you could actually predict the products. Again, the easiest would be number one. It's just the opposite example that we use for the combination. Instead of a metal and a nonmetal producing an ionic compound, we have an ionic compound breaking down to the metal and the nonmetal. Now, in this next example, you'll see that this is very similar to the example number 3, where what do I have? I have a metal chlorate, and if you recall, that broke down to what? Metal chlorides and oxygen gas. So seeing that this is potassium chlorate, I would know that the metal chloride would be potassium chloride, and it's an ionic compound, so it's solid at room temperature, and it's going to also give me oxygen gas. So again, what do we notice? One reactant, two or more products. Now the next thing we have to do is we have to balance this. So if we go through the rules, rule number 1, we have one potassium, one metal, one potassium. Rule number 2, go to nonmetals, one chlorine, one chlorine. Chlorate's not on both sides, so I have to break it up to its elements. That's why I went to chlorine. And then last, I save the oxygen, and I look, there's 3 oxygen here, and there's only 2. So I have to find a common denominator for 2 and 3. And that common denominator is 6. So I need 6 oxygen on both sides. So what am I going to multiply 2 by to get 6? 3 what am I going to multiply 3 by to get 6? 2. Now this coefficient of 2 in front of the potassium chlorate changes how many potassium I have, so I just go back, I put a 2 there, and I'm